So this video is going to be on lesson 1.3, graphs of functions. We're going to talk about finding the domain and range, looking at a graph or looking at it algebraically. We're going to talk about the vertical line test, how you can look at a graph and determine whether it's a graph of a function. And we're going to look at how these functions have intervals over which they may be increasing, intervals over which they may be decreasing, and specifying which intervals it's increasing or decreasing. So let's start with this basic idea of a graph. Let's make sure we understand that this particular graph, or any graph, every point on this graph is an ordered pair where you have an x value as the input and then a function value as the output. It's the same as the familiar x-y ordered pair, except we're using function notation instead of the xy notation. Now, so the x-axis, the horizontal axis, is going to have the domain values. The values that go in for x are the domain values. So domain has to do with the x values, and then the range values, in other words, the outputs, the function values, will have to do with the f of x, or the y-axis. If you take the set of all the x values from these ordered pairs, that would be the domain. And if you had a set of all of the f of x values for every point on this graph, that would be the range. So what I'd like to do is describe the domain of this graph right here. And what I see is the x values that are used in this graph start at -2 and include -2. So let me write it like this in using interval notation. They go all the way from -2. They don't go any further this way. Notice at -3, for instance, there's not a point on that graph that has -3 as an input value, as an x value. So, but starting here at -2 and then moving this way, every one of these points has an x value. For example, let's say, I don't know, it looks like this point here has an x value of -1 and then a y value, or f of x value, of -2. In other words, that would be the point -1, -2. But the point is, that spot on the graph has an x value associated with it. And notice that this graph, as you move to the right, keeps going. It keeps going. We have to stop drawing it. But it doesn't stop right here. It keeps going. So forever this direction on the x-axis, there's going to be an x value, and then it's going to go to the graph and correspond with a y value. So it's part of the domain, I guess is what I'm trying to say. So it goes forever this way, so to infinity. And that would be how we would describe the domain of this graph. From -2 and including -2, all the way to positive infinity. Okay? Now, the range has to do with the function values that the graph has. And so that's going to have to do with this vertical axis. And what I noticed is it bottoms out right here at -2. This is the smallest y value this graph ever has. So we can say that, and just a coincidence that it's also at -2 like the domain was. But notice it bottoms out here. But as you move up, it goes to infinity. And again, just a coincidence that those worked out to be the same. They certainly wouldn't have to. Just happened to be the case in this example. So what we've done is we've looked at this graph and looked at which x values are at play. That's the domain, and then which y values are at play. That's the range. Now, just another quick example. What if we had something like this? This would be well, and suppose let's say it stops right here, and let's say that's at 3, 3. That's at 3, 3. Now, so this time, here's our x-axis, f of x, domain. What are the x values that are used on this graph? What about -2? Is it used? No. What about 1? Is it used? Yes, because notice that 1 hits the graph and it is associated with a y value of 1. In other words, that's the point 1, 1. What about 4? Well, no, because the graph stops here. If you were to go vertically up from 4, you don't hit the graph. If you were to go vertically up or down, from -2, you don't hit the graph. What about -1/2? Yes, so it is used. It is part of the domain. What about 1/2? Yes, so it is part of the domain. So, in interval notation, we would say that the domain goes from -1, and notice this time it does not include -1 itself, it's just up to -1. And so I use the parentheses instead of the brackets. And then it also has a right endpoint of 3. So the domain in this case, I'm sorry, this should be a bracket. So the domain in this case are going to be all of the numbers from -1 to 3. From -1 to 3. Anything outside of 3 is not part of the domain. Anything to the left of -1 here is not in the domain. What about the range? Well, let's see. Looks like in terms of the y-axis, it gets as low as 0. And it gets as high as 3. There's no y value. In other words, if we were to draw a horizontal line up here at, say, 4, you're not going to hit that graph. If you were to draw a horizontal line down here at, say, -1, you're not going to hit that graph. It's only from 0 to 3 where you're going to have y values. It's only from -1 to 3, and not even including -1, the endpoint, that you're going to have x values. So this has to do with the domain and the range. Domain are the values that you can input into the function, and the range are going to be the values you get from those inputs. So let's talk for a moment about the vertical line test. And this is used to determine whether what you're dealing with is a function. So let's say, for instance, you had a graph. I'm talking about looking at a graph, applying the vertical line test to see if it is a function. So let's suppose we had maybe just a line. And we're wondering, well, is this a function? Well, to apply the vertical line test, what you have to do is try to determine whether a vertical line could hit this graph in more than one place. So if I just start randomly looking at vertical lines, this one would hit the graph once, this one would hit it once, this one would hit it once, this one would hit it once, and in fact, there's nowhere you could draw a vertical line that would hit this line right here more than once. So what we would say is this passes the vertical line test. It passes the vertical line test, which means it is a function. It is a function. What this is showing us, what this is demonstrating visually, is that every x value, like for instance, this x value here, is paired with one and only one function value, or y value. That's what the test is trying to determine for us. Because if a vertical line can hit the graph in more than one place, as we'll see in the next example, that means there is a particular x value, domain value, that is paired with not just one, more than one range value. And by definition, that would not be a function, and the vertical line test would expose that reality. All right, so let's look at an example like that one. Let's suppose we had, I don't know, this graph right here. On this graph, notice I could draw a vertical line, say, I don't know, here. And notice that this point and this point both have the same x value. Whatever this x value right here is. They both have that x value. Let's suppose it's 2 right there. So the ordered pair for this point is going to be 2 something. But notice this one also is 2 something. Okay? I don't know. Let's suppose this is at -2, and this one's at 2. So we would have 2, 2, and 2, -2. And what this is showing us is we have the same domain value, the same input value of 2, but it leads to 2 different range values, 2 and -2. And this fails the vertical line test. Vertical line test. It is not a function. It is not a function. So that's what we mean by the vertical line test. Can a vertical line hit the graph in more than one place? If it can, it's not a function. But if a vertical line can only hit the graph in one place, no matter where you put that vertical line, then it is a function, and it's demonstrating that every x value, every domain value is paired with exactly one range value, and that's the definition of a function. So let's talk about increasing and decreasing. Let's go back to this first example. When we talk about increasing and decreasing, we're talking about the function values. As your domain values are increasing, what are your function values doing? Are they going up? Are they going down? Are they staying constant? And notice that on this particular graph, as you move from -1 all the way to, I'm sorry, I was looking at this -1. As you move from -2, that x value -2, all the way over to the x value of -1, on that interval, the y values, the function values, are going down. So it's decreasing. However, at that point, it changes. Now, from -2 all the way to infinity, the function values are increasing. So I guess the main point here is to understand that these functions can have intervals over which they're going up, they can have intervals over which they're going down, they can even have intervals over which they're moving horizontally, so they would be constant over those intervals. So, and one thing I forgot to do when we were talking about domain range, so let me kind of back up a little bit. When we were first talking about the domain and the range of this one, the very first thing we talked about, we were looking at the graph and making those determinations. But sometimes we're given a function algebraically, in fact, very often. So suppose we had this function right here. We're not given the graph of it. We're given the equation. If we want to figure out the domain and range of this, then what we need to do is recognize, in a mathematical sense, what would limit us in terms of what we put in for x. If there's no limitation on what you can put in for x, then the domain will be all real numbers. And a lot of times that is the case. But in this particular problem, it's got a radical in it. And one thing that we know is we don't want a negative. Can't have negative under the radical. That's the mathematical fact that's going to be real important in this problem. If you have a negative under the radical, then you move into the realm of complex numbers. And we're working in the real numbers. So the limitation here is that the quantity under the radical here can be negative. That wouldn't be a valid domain. Any x value that gives us a negative under the radical is not going to be part of the domain. So think about it. What we're saying is that this quantity x minus 9 needs to be non-negative. And the way you would say that mathematically is it needs to be greater than or equal to 0. Now, we can solve this inequality so that it's specifically talking about x, by adding 9 to both sides of it. And you find that x has to be greater than or equal to 9. And that kind of makes sense. As long as x is 9 or more, you can see that this would be a positive number under here. If it was 9, you would have 0. And the square root of 0 is fine. If it was 20, easily a positive number under here. But what if it were 8? Well, then you would have the square root of -1. And again, that's going to be a complex number. We're working in the real numbers. So by understanding this fact about radicals and then just expressing that fact, the fact that this needs to be non-negative, like so, allows us to see that the domain in this case is going to be from 9 to positive infinity. It's going to be the domain. As long as we pick a number from 9 to positive infinity, we can plug it into that, no problems. And we'll get a function value will pop out, and together they'll make an ordered pair. So another situation that comes up a lot is going to be, maybe you have something like this. And again, we're going to have a limitation on the domain here as well, because when you've got a variable in the denominator, you have to look for the possibility that you could get a 0 in the denominator. Division by 0 is not allowed. So in this case, we know that x minus 4 cannot be 0. X minus 4 cannot be 0. So any value where x minus 4 is 0 is going to be excluded from the domain. So in other words, if we were to solve this, and we see that x is 4 is what would make us have a 0 in the denominator. So we can say that the domain is going to be all x except x equals 4, or we could use interval notation, and we could say from negative infinity all the way up to 4, but not including 4, and from 4, not including 4, to positive infinity. There's different ways we can do it, but we just have to understand that 4 is not going to be part of the domain for this function. 4 is not going to be part of the domain. It would give us a 0 in the denominator.